Dear children, today we can go through the next chapter, chapter 10, Mechanical Properties of Fluids. In this chapter, we are going to study about some common physical properties of liquids and gases. We can see some introductory part of this lesson. In the lower classes, you studied about the fluid. So, what do you mean by fluid? Anything that can flow. Okay. Liquids and gases can flow. So, they are called fluids. This property distinguishes the liquids and gases from solids. And you know that fluids are everywhere around us. Earth has an envelope of air and 2/3 of its surface is covered with water. Okay. Fluids have no shape of their own. Solids and liquids have a fixed volume, whereas a gas fills the entire volume of its container. Clear? And volume of solids or liquid or gas depends on the stress or pressure acting on it. When we talk about the fixed volume of solid or liquid, we mean its volume under atmospheric pressure. The difference between gases and solids or gases and liquids is that solids or liquids, for solids or liquids, the change in volume due to change of external pressure is small. In other words, we can say that solids and liquids have much lower compressibility as compared to gases. This you studied in the chapter Mechanics of Solids. Okay. And one more thing, that shear stress can change the shape of a solid, keeping its volume fixed. But the fluids offer very little resistance to shear stress. Their shape changes by the application of very small shear stress. Clear? So, this is some introductory part of the fluid. Now, we will start the chapter with the pressure. So, what do you mean by pressure? Pressure means force per unit area. P equal to F by A. For example, before going to the concept of this pressure, we can see some example. For example, a sharp needle. You take a sharp needle and when it is pressed in your skin, what happens? It pierces into the skin. Because here the area is very small. Okay. The area of contact is very small. So, it pierces into your skin. But when you take that means when you take this pen and when you press it in your skin with the same force, then what happens here? It does not pierces and it does not be painful. In the first case, when you take the needle and when you press it into your skin, it makes painful. Because the area of contact is small, so the pressure is greater. In the second case, area of contact is large. So, here the area of contact is large. So, the pressure is small. So, the pressure is determined by the two important things, that is the force and the coverage area. Okay, pressure is determined by force and coverage area. So, area is very small, then the pressure is large. It makes painful. Okay, with this example. If the area is very large, pressure is small. Okay. So, this is the concept of pressure. Force exerted on a unit area, that is known as the pressure. Then what do you mean by the pressure on fluid? For example, you look at this figure. Here an object is immersed in a fluid at rest. The fluid exerts a force on its surface, and that force is always normal to the object surface. If there is a component of force parallel to the surface, then the object will also exert a force on the fluid parallel to it. That is according to the third law. This parallel force causes the fluid to flow. Here the fluid is at rest, so this cannot happen. Hence, the force exerted by the fluid at rest has to be perpendicular to the surface in contact with it. This is shown in the figure A. Then the second figure shows the one measuring device, pressure measuring device, figure B. It consists of an evacuated chamber with a spring. That spring is calibrated to measure the force acting on the piston. The device is placed inside the fluid. Okay. So the inward force exerted by the fluid on the piston is balanced by the outward spring force, and it is measured by that calibrated spring. So look at the figure. F is the magnitude of the normal force on the piston of area A. So the average pressure P we can define as the normal force acting per unit area. Okay, average pressure P is defined as the normal force acting per unit area. Clear? That we are writing here, that is the P equal to F by A. If the piston can be made to be, that means piston area of the piston is very small, then the pressure is then defined as a limiting value. Then we can write P equal to, okay, P equal to limit delta A tends to 0, delta F divided by delta A. So this represents that area of the piston is limiting to be very small. So P equal to limit delta A tends to 0, delta F change in force divided by delta A. Clear? Then pressure is a scalar quantity and its unit is Newton per meter square, and it has been named as Pascal. It is a symbol, that is a PA. You know this. The dimension ml raised to minus 1, T raised to minus 2. Then there is a common unit of pressure is there, that is the atmosphere, represented by ATM. 1 atmosphere equal to 1.013 into 10 raised to 5 Pascal. So I think you understand about the pressure. Clear? Pascal's law. The pressure in a fluid at rest is same at all points if they are at the same height. That is the Pascal's law. To explain this, we can see one example. So you look at this figure. You consider a small element A, B, C, D, E, F, that is shown in the figure in the form of a right angled prism that prism is in the interior of the fluid at rest. Okay. And the element is so small that all parts can be assumed to be the same depth from the liquid surface. The element is so small, so we can assume that all parts can be assumed to be at the same depth from the liquid surface. Therefore, the effect of gravity is also same at all points. Okay. Suppose the fluid exerts pressure PA on the face BE BEFC. You look at the face BEFC and pressure PB on the side ADFC and pressure PC on the side ADEB on the element. Okay. Therefore, the corresponding normal forces on these faces are FA, FB and FC. That is also shown there. Let the area of the three faces are AA, AB and AC. So, from the right angle triangle, you just take the right angle triangle ABC. Let angle AC be equal to theta. Okay. So, the element is in equilibrium with the fluid. So, the fluid force should balance in various directions. That force is shown on the prismatic element. Clear? So, in the equilibrium condition, from the figure we can write sin theta. Okay, sin theta equal to FC by FB and cos theta equal to FA by FB. That is according to the equilibrium condition. Similarly, by geometrical method, we can write from the figure sin theta equal to AC by AB and cos theta equal to AA by AB. Clear? So, these two equations, that is four equations are written from the figure. The first two according to the equilibrium condition and the second one by the geometrical condition. So, we can write here FB sin theta equal to FC. So, already I told sin theta equal to FC by FE. So, FB sin theta equal to FC. Similarly, FB cos theta equal to FA. This is according to the equilibrium condition. And from geometrical condition, AB sin theta equal to AC and AB cos theta equal to AA. So, from these two equations, we can write FB by AB equal to FC by AC. That is also equal to FA by AA because cos thetas and sin thetas will cancel. So, what is FB by AB? That is equal to pressure. FC by AC, pressure at the side C and FA by AA, pressure at the side A. So, what does this prove? This activity proved that pressure exerted is same in all directions in a fluid at rest. That is PA equal to PB equal to PC. Okay, the pressure exerted is same in all directions in a fluid at rest. Clear? So, this proves the Pascal's law of transmission of fluid pressure. Clear? Variation of pressure with depth. You should find out pressure at a depth inside a container. So, for that, for finding out the expression for the pressure at a depth, we are considering a fluid at rest in a container. There, you consider 2 points. Inside the fluid, you consider 2 points, 1 and 2. And the point 1 is at a height h from the point 2. With this point, you consider a cylindrical element of height h and the area A. The force exerted, that is the horizontal forces exerted on the fluid at the two ends, that is the two horizontal forces are equal and opposite, so they must be 0. Then the vertical forces exerted on the fluid element must be equal to this weight of the fluid element. So we can say that the fluid is at rest. Okay, why fluid is at rest? The horizontal forces should be 0 and the resultant vertical forces should balance the weight of the element. Okay. So, the forces acting in the vertical direction. Okay, the forces acting in the vertical direction are due to the fluid pressure at the top acting downward. So, So what is the force at the top? That is pressure at the point 1 into the area, that is the P1A, that is acting downward. And what is the force acting in the upward direction? That is the pressure at the point 2 into the area. So that is acting in the upward direction. So once again, the force acting in the downward direction along the fluid element is P1A, and force acting in the upward direction is P2A. It is equal to, that is the resultant of these two forces must be equal to the weight of the fluid element. So we can write the equation here, P2A in the upward direction, P1A in the downward direction. So we can write P2 minus P1 into A. Okay. So that is P2 minus P1 into A. It is equal to the weight of the fluid element. Clear? That we can note it as equation number 1. Then if rho is the density of the fluid, then V is the volume of the fluid, then what is the mass of the fluid? M equal to density into volume. So what is the volume of the fluid? It is equal to the fluid element, that is equal to the area into the height h. Clear? So we can write rho into h into A. This is the mass of the fluid element. So we can write the pressure P2 minus P1. We can substitute this M in the equation number 1. That is P2 minus P1 into A equal to rho H A into G. And A we can cancel. Then what is remaining? P2 minus P1 equal to rho GH. So this is the pressure difference on the fluid element. Clear? P2 minus P1 equal to rho GH. So this pressure difference depends on the vertical distance h between the points 1 and 2. That is the height of the fluid element and density of the fluid and acceleration due to gravity. Okay. So by considering this fluid element, we find out the pressure difference between the top of the fluid element and bottom of the fluid element. That pressure difference depends on rho, G and H. H is the height of the fluid element. So you want to find out the pressure at a depth, isn't it? So for that, we can assume that you just take this point 1 to the top of this fluid that is open to the atmosphere. You consider this point 1 on the top of the fluid that is open to the atmosphere. So what is the pressure at this point? In this case, that is P1 equal to the atmospheric pressure. If the point P1, we will consider, if you consider the point 1 on the top of this fluid surface, then that P1 is equal to the atmospheric pressure. Okay, and this point P, that is point P2, that means the pressure at the point 2, that we can note it as only the pressure P. Then this one we can apply in the equation number 2, that is P minus PA equal to rho GH. Clear? So this point 1 is at the top of the fluid, that is at a distance h from the point 2. Okay. So with the, by that consideration, we written that P minus PA equal to rho GH. P is the pressure inside the fluid. So we can write pressure inside the fluid at a height h from the surface. When the point P is shifted to the top of the fluid, then height h is from this point to this point. So the pressure at the point P, okay, is equal to the atmospheric pressure plus rho GH. This is the pressure at a depth below the surface of the liquid open to the atmosphere. Okay, that is pressure at a depth P equal to PA plus rho GH. So that pressure is equal to, or that pressure must be greater than the atmospheric pressure by an amount rho GH. Once again, the pressure P at a depth below the surface of the liquid open to the atmosphere is greater than the atmospheric pressure by an amount rho GH. Clear? So this is the equation to find out the pressure at a depth. So pressure at a depth is greater than the atmospheric pressure by an amount rho GH. Clear? Then this P minus, so this P minus PA, okay, P minus PA equal to rho GH. So this P minus PA is known as the excess pressure. Okay, so the excess pressure at a depth P minus PA is known as the gauge pressure at the point. So what is this P minus PA? That is the pressure difference at the top of the fluid and at the depth, that is at a distance h below the surface of the fluid. So this pressure difference, that is P minus PA, that is the excess pressure and it is known as the gauge pressure at that point. Okay, P minus PA is known as the gauge pressure. So in this way we can find out the pressure at depth. Clear? Another one important point related to the liquid pressure is it is same at all points at the same horizontal level. We can see this with an example of hydrostatic paradox. The figure shows the example of that hydrostatic paradox. You consider three vessels A, B, C as shown in the figure of different shapes. They are connected at the bottom by a horizontal pipe. Then you fill the water in three vessels. Though they hold different amount of water, but the level of the liquid is same in all the vessels. This is so because water at the bottom has the same pressure below each section of vessel. So we can say that the liquid pressure is same at all points at the same horizontal level. Because of this reason, if the vessels have different shape, though they hold different amount of water, the level of the liquid in three vessels is same. Clear?